Well, first of all, there was a question about one of the sections and examples in the textbook. It was about the example given for non-holonomic constraint. So, well, first of all, broadly, what is holonomic constraint versus non-holonomic? Holonomic constraint is a relation between the coordinates, and that can be expressed as a simple equation. Let me see if I can give an example. Yes, okay. Well, let's see, is that the best example? Yeah, okay, sure. An example would be if we look at, okay, yeah, a very simple example would be if you just look at a simple pendulum, and we know that it's constrained to move on the arc of a circle. And so we have this constraint that if this is some length L, then the constraint is R equals L. Or we could write that as R minus L equals 0. That's a very simple constraint. One level up would be if you have, say, a cylinder rolling without slipping in 1D, right? Just along this ramp. Then if you look at the angle through which it turns, so let's call that theta, and let's call the distance that it rolls, let's call that z, then say that this is some radius r. What's the relation between z and theta? Anyone? Oh, there's chat windows. Where in the text is this? Oh, okay, you got it, page 249, cool. So what relation do we have between between z and theta?
Z equals r theta.
Z equals r theta, exactly.
Yeah.
So if we have rolling without slipping, we have z equals r theta, and we're more familiar with this in, it's like if we take the derivative, r is a constant here, so that stays like that. So then we basically are getting like vz equals omega r, right? And we're familiar with that. If we take one more derivative, we can go to az equals alpha r. So these are examples of holonomic constraints. And as I said, they're basically constraints that can be stated in a simple equation of the coordinates. So if you have generalized coordinates q1, q2, etc., you just have some function of q1, q2, etc. is equal to 0. But what's important is no velocities involved. So most of the time we'll be dealing with holonomic constraints, but occasionally you do have non-holonomic examples. And one example that was given in the textbook was if you have a ball that's rolling on a plane, then it ends up that you need more than 2 degrees of freedom to describe the ball. And unfortunately, I did not have a handy spherical ball available, so I improvised with the little paper ball. And the idea is that if you roll the ball, so I'm starting here with the green dot on top, you roll the ball through one path, and then, yeah, this is not going to be a very good illustration because it's slipping, obviously. But then, and you bring it back through a different path. to the starting point, you see that it doesn't come back to the starting configuration of the ball. That proves that it's not enough to know where the center of the ball is. You also need to know the orientation of the ball about the center, right? So you need two coordinates. It's rolling on a plane, so x and y will give you the coordinates of the center of the ball, and then you need three more angles to describe how the ball is oriented about the center. So that makes for a total of 5 different coordinates in all. So there are relations that can be made for the angles and x and y and how they're related to each other, but they can't be expressed as this sort of equation. Instead, it's more a relationship between dx, dy, d theta, d phi, so on. And those relations can't be integrated into a relation like this. If they can, then it would be a holonomic constraint. But if they can't be integrated, if they're just a set of relations among the differentials of the coordinates, or if they're relations between the velocities in the coordinates, then those are non-holonomic constraints. But mostly we won't be dealing with those. Questions? Okay. What I'm planning is that I'll go through a few different examples, just showing a few different features that come up. And yeah, we'll discuss the examples, and we'll see how much time is left after that. Okay, so back when we're doing like physics 113 or mechanics, intro mechanics and so on, standard problem was if you have a ramp and you have a little mass on the ramp and it's frictionless and it slides down. So you have some little mass and it's just sliding down the ramp. The ramp has an angle, say alpha, and you are trying to try to determine the motion of the box sliding down. And but in all those examples, the ramp was fixed. And the next level of complication is, oh, well, what if the ramp itself has some mass capital M and is on a frictionless floor? Then as this slides down to the right, then the ramp itself is going to start moving to the left. So how do we solve for the motion of all the particles involved? So this has been covered in the textbook as one of the examples. I'm first going to show how you would set it up using Newton's laws, right, the old mechanics way, and then briefly talk about the Lagrangian method of doing it. And yeah, feel free to interrupt anytime you have a question. All right, so if I'm doing it using forces, then first thing I should do is draw a free body diagram. So I'll have a free body diagram for little m. And what are the forces acting on it?
Gravity.
Gravity, yep. So I'll have little mg.
Normal force.
Normal force. So there's a normal force from the wedge on the block. So that's going to look something like this. And we're going to have another normal force later, so I'll just call this Fn1. Okay, and we're setting up our axes as usual. We have x and y. And so in this case, there is an acceleration both in the x direction and in the y direction, and we'll get to that later. All right, so those are the forces on the little mass. What about on the wedge?
You have
Harold.
who was talking? Well, I was going to say you have that same normal force pushing down on it in the opposite
Yeah,
direction.
so we have Fn1 in the opposite direction. What else?
We would have a normal force pointing up from the ground.
Exactly, yep. So I'll call that Fn2.
Gravity.
Gravity, yeah. So we have capital Mg over there. Okay. And in this case, we know there's no vertical motion, so we know there's just going to be an acceleration in the negative x direction. Okay, so let's set up the relevant equations. I need the angle alpha in there as well. So over here, alpha would be this angle, and over here, it would be this angle. All right, so now I can write the equations. So here in the y direction, I have Fn1 cosine alpha, minus little mg is equal to little m times ay. And in the x direction, I have Fn1 sine alpha is equal to little m times ax. All right, over here I have, in the y direction, I have Fn2 minus Fn1 cosine alpha minus mg is equal to 0. There's no acceleration in the y direction here. And then in the x direction, I have minus Fn1 sine alpha is equal to capital M. And I need the acceleration of big M, so I'm going to call that capital AX. Okay. So if we look at the number of unknown quantities, we have AX, capital AX, we have little ax, we have little ay, so it's 3 of them, and then we have Fn1 and Fn2, right? We're assuming that we know what the two masses are, and we know the angle, and we know g, but that still leaves us with 5 unknowns and only 4 equations. Oh, by the way, one feature I should point out. Well, one thing is that I'm recording this, so I mean, don't worry, I'll post the recording. The other thing is, I believe if you use the annotate bar, then you can take a screenshot, I think, using that. All right, so 5 unknowns, only 4 equations. So we need one more equation to help solve things. So for that, what we do is we kind of go back to our diagram and let's add a little bit more structure. So let's say that our origin is over here, and let's call this distance capital X, right up till the edge of the wedge. What do we need? Right, let's call this the height of the wedge, let's call that h. And we need to talk about the position of the block. Okay, so how do I want to set it up? Yes, okay. So we'll call this distance here up to the block little x, and we'll call the distance above the ground little y. All right, so then this distance here is going to be h minus y. Okay, and so then this is another little triangle with angle alpha. So if this is h minus y, we can figure out what this distance is. So I'm really doing it to like the edge of the block, but that's sufficient for our purposes. So then this little distance is going to be related to h minus y through tan of alpha. So I can say that, let's see, it's going to be a little hard to, okay, I'll just write it above actually. I can say that little x minus capital X, so that will be this distance, is going to be equal to h minus y divided by tan alpha. Questions?
Is big X the initial position then of the
No, big X.
wedge?
No, it's the position of the wedge. So it's going to be a function of time.
Okay.
Okay. So how do we use this relation? Well, we can take a derivative with respect to time. So alpha is a constant and h is a constant. So when we take derivatives, we first end up with, so I'm going to move that off screen. We're first going to end up with little x dot minus big X dot is equal to minus y dot over tan alpha. And then we can take one more derivative. And well, if we take one more derivative, we're going to get the acceleration. So we get ax minus big Ax is equal to minus ay over tan alpha. All right, so now we have 5 equations and 5 unknowns, and so we can start eliminating those one by one. Well, we can solve for all of them.
Could you briefly go back up to the setup?
Yep.
I just missed some of the. Great. Thanks.
Yep. Any other questions? Okay. So how do we approach this in the Lagrangian method? Well, as usual, we should decide first what our generalized coordinates should be. So to describe what's going on, well, we'll definitely need something like capital X, sure. And then the block is sliding down the wedge. So we could define a coordinate that goes from the top like this, and for lack of a better coordinate, I'll just call it Z, even though it's not really X, Y, Z. So yeah, so that's really all we need to know, right? We just need to know, okay, where is the edge of the wedge? And then how far down the wedge has the block slid, right? And that'll be sufficient to place this system in a particular configuration. All right, so we have 2 generalized coordinates. So we can try and set up the Lagrangian. So we know that Lagrangian is equal to kinetic minus potential. And so the kinetic, we're going to have 1/2 m little v squared and also 1/2 m big V squared. For the potential, there's gravitational potential energy, and only the little block is changing its y position. So we'd have minus mgy. And then we translate all of this into terms of 2 general coordinates. So we'll start off with little v little v squared is equal to x dot squared plus y dot squared. And then we need to express these in terms of big X and Z. So if we go back to our picture, let's yeah, let's see what we can get. So how does Z fit into this picture? Well, we can see that, yes, H minus Y over Z is equal to, so that would be opposite over hypotenuse, is equal to sine alpha. And similarly, this is little x minus capital X. So that over Z, so little x minus capital X over Z is equal to cosine alpha. So we can solve for Y in terms of Z and, well, in terms of Z, and little x in terms of big X and Z. All right, so let me do that. So we have H minus Y is equal to Z sine alpha, and we have little x minus big X is equal to Z cosine alpha. And so then if we take derivatives, we have Y dot is equal to minus Z dot sine alpha. And we have X dot is equal to big X dot plus Z dot cosine alpha. Oh, and also, of course, stop me if I make any mistakes. All right, so then I have to square these and so on. So if I do X dot squared, I'm going to get big X dot squared plus Z dot squared cosine squared alpha plus 2 X dot Z dot cosine alpha, and Y dot squared is going to give me Z dot squared sine squared alpha. So I can see there's going to be a sine squared cosine squared thing going on. So this little V squared is going to end up as big X dot squared plus Z dot squared plus 2 Z dot X dot cosine alpha. That's little V squared. Big V squared is just X dot squared. It's only moving in the X direction. And then for Y, we've already seen here that Y is equal to H minus Z sine alpha. So we can put all this together to get our expression for the Lagrangian. So we have L is equal to 1/2 little m X dot squared plus Z dot squared plus 2 Z dot X dot cosine alpha plus 1/2 big M X dot squared, and then minus mg H minus Z sine alpha. All right, so we see that we have two general coordinates, Z and big X. And so we can write the Euler-Lagrange equations for Z, Euler-Lagrange equation for big X, and we can solve and describe the motion.
On the left side of your page, where you have V squared equals X dot squared plus Z, and then that next time you say V squared equals X dot squared, is that the one right below that?
This one?
Is that big, yeah, is that big X dot?
Yeah, that's big X dot and big V, yeah.
Okay.
Because the wedge is only moving in the X direction.
Yeah, it's so hard to tell with the different X's.
Yeah, no, that's fair. Oh, that's what I should use cursive for the little one. Yeah, okay, too late now, but yeah. All right, so that would give us our equation. So the advantage of the Lagrangian method is that you don't have to worry about, I mean, you assume basically that the conditions are satisfied, that, that the block is sliding on the wedge. You don't worry about what's enforcing the block to move on the wedge, which is basically the normal force and gravity. A certain combination is keeping them in contact. And so that's advantages because you don't have to worry about all the internal forces and the normal force and all that. You're only concerned with the forces that are actually doing work on the system, which in this case would be a component of gravity. So yeah, so that's the advantage of the Lagrangian method. But sometimes you do want to know about the forces, right? Sometimes you do want to know about the forces that enforce your various constraints, right? So if you have rolling without slipping in 1D, right? So what force is enforcing rolling without slipping?
Friction.
Friction, static friction, right? If there's no sliding going on, then if there's proper gripping going on there, then that must be static friction. So maybe we want to find out what the magnitude of the friction force is. Maybe we want to find out what the magnitude of the normal force is, and so on, or the tension in a string. So it turns out that if you do want to find out the values of those forces of constraint, there is a method in the Lagrangian way to do that. So I'm going to show you a couple of examples that build off of, that use that method. Okay, I'm gonna turn the page. All right. So the method is, it's a person we've already met before, Lagrange again. So the method of Lagrange multipliers. And so the idea is that, oh, it's not focused. There we go. All right. The idea is that you make a trade-off, and it'll be simplest with a concrete example. So let's say that I'm looking at the simple pendulum. Now, really, all I need to describe this is the angle theta. But we said that I could also think of it as there being a constraint on R, right? I could say that R has been constrained to be little l. So let me use that. So what I do is I've reintroduced a coordinate that's actually fixed, right? And I'm going to write my Lagrangian. So I have L, yeah, okay. I'm going to have L is equal to T minus U. And so that's going to be 1/2 mv squared minus mgy. So I need to fix my origin. So I'll make my origin up over here and the usual directions for x and y. Okay, but I'm working in polar coordinates. So my 1/2 mv squared is going to, my v squared is going to have two terms. It's going to be r dot squared, and there's going to be r times phi dot the whole squared. So that's now my kinetic energy in polar coordinates. And for y, I'm below the origin, so I'm going to have a negative value for y. So y would be minus r cosine, oh, I said theta and phi. Let me call this phi. All right. So my value for y would be minus r cosine phi. But then I already have a minus sign here, so that will altogether give me plus mgr cosine phi. So I reintroduced r as a generalized coordinate. So I have this expression, but now I want to enforce this constraint that r is equal to L. So what I do is I construct a new Lagrangian, let me call that L prime, and it's simply equal to my Lagrangian plus lambda times f. All right, so what's going on here? Let me clarify. So lambda is a function of time, so it's lambda of t, and it's called the Lagrange multiplier. F is a holonomic constraint. So it is a constraint that can be written purely in terms of the coordinates. So in this case, and the idea is that you write it in the equation form f equals 0. So in this case, this would be r minus L is equal to 0. And so with those modifications, my new L prime is going to be, well, first just L. So r dot squared plus r phi dot squared plus mgr cosine phi plus lambda times r minus L. So this is my new L prime.
This will probably be revealed later on, but
yeah, go ahead, ask.
But if r is fixed at L, what is the point of adding on the multiplier?
Right.
It's just going to be multiplied by 0.
Yeah. So by delaying the enforcement of the constraint, what we're going to see is that the value, the expression that we get for lambda, so lambda, we're introducing a new unknown, and it turns out that the value of lambda ends up being physically relevant. Okay, so you're completely correct that, I mean, like the normal way to do this would be to go back to this Lagrangian and say that, oh, well, r is actually fixed at L. So we could replace this with L. We could say that r dot is 0, so this term would go away, right? So that's definitely a way that you can do this, okay? And that will give you the correct Euler-Lagrange equation for phi. But we are going to make a slight trade-off and make the procedure a little bit longer, but get a bit more information. All right, so,
I see.
Yeah,
Thanks.
I mean, it'll become more concrete once we go a bit further. All right. Okay, so now we have, so we have two generalized coordinates. We have r and phi now, and we also have the constraint equation. So we're going to have three equations, and we have essentially sort of three unknowns. We have r as a function of time, phi as a function of time, and lambda as a function of time. So let's see what we get. So for phi, if I do the Euler-Lagrange equations, I have partial L partial phi is equal to d by dt partial L partial phi dot. So partial L partial phi will only get a contribution from here. Derivative of cosine is minus sine. So I have minus mgr sine phi. All right. And then on the right-hand side, I have d by dt of partial L partial phi dot. There's only one phi dot term. And so I have m r squared phi dot here.
Don't you need
quick
a
question.
phi dot on the left side as well?
Yeah.
On the chain rule.
A phi dot.
Sine phi times phi dot.
Here?
Mm-hmm.
Oh, I'm not differentiating with respect to time. I'm just differentiating with respect to phi.
Oh, right.
So, I mean, you're correct that like when I apply this d by dt over here, I'm going to pick up like an r dot term and a phi double dot term. Those are going to be there, yeah. But on this side right now, I'm just doing a partial with respect to phi, so. All right, so that's one equation. What about for r? So for r, I have partial L partial r is equal to d by dt partial L partial r dot. So now I'm going to pick up some extra stuff from this constraint term. All right, so partial L partial r, I pick up one term from here. So I'll get m, what's it going to be, r phi dot squared. And then another one from here, plus mg cosine phi. And then another one from here, plus lambda. So that's all partial L partial R. And then equals d by dt of, and so r dot only appears here. So I will get mr dot inside here. So any questions before I flip the page?
So does L prime doesn't represent the time, it's not the derivative of
Yeah, sorry, yeah, it's not a derivative of any kind of L. I could just call it L nu if you like.
Okay.
Yeah, so I'll just say L nu is old L plus lambda f. Other questions? So yeah, so this should be L nu in here. I should clarify that. Okay. All right, so what are the equations we have now? Let me just copy them and, well, actually, yeah, you can actually probably see them. All right, so one of the equations is minus mgr sine phi equals, let's see, m r squared phi double dot plus 2 m r dot phi dot. Okay. And then the other equation, so let's call that equation 1. Equation 2 is m r phi dot squared plus mg cosine phi plus lambda equals m r double dot. And then our third equation is the constraint, r equals L. All right, with me so far? I'll take that as a yes. So, okay, so now we start applying the constraint. Okay, and that's going to make life a lot simpler. So since r is equal to L, which is a constant, that immediately gets rid of any derivatives of r. And anytime we see r, we can just replace it with L. So using equation 3, for example, equation 1 is going to become minus mgl sine phi equals ml squared phi double dot, and then this term goes away because r dot is 0. Equation 2 is going to become ml phi dot squared plus mg cosine phi plus lambda is equal to 0 because r double dot goes away. All right, I can simplify these equations a little bit. So this equation becomes the familiar equation for the simple pendulum. You get phi double dot is equal to minus g over L sine phi, right? So it's just, if you use a small angle approximation, becomes simple harmonic oscillator. But if you don't, you have the sine phi there. All right, and over here, so this equation alone is already enough to solve for phi as a function of time. Okay, so we know phi is a function of time. We know r is a function of time, it's a constant. And so then the last thing is lambda. All right, so we can solve for lambda, and what we get is lambda is equal to minus mg cosine phi minus ml phi dot squared. All right, well, what was the point of that? So there is a physical interpretation to this lambda. Let's think about what it's doing. It's picking out a component of gravity, of the force of gravity, and it's picking out ml phi dot squared. But if we think of phi dot as omega, then, and L as being like the radius of the circle it's moving in, and this is basically m r omega squared. But that's just centripetal. So altogether, this is actually the force of tension, which is the constraint force, which is enforcing the motion along that circle.
Could you explain again why it's the force of tension? Like, could you make that more explicit?
Sure. So if I draw the diagram, so this is phi, and let me draw the free body diagram. So the free body diagram will have mg down like this. It will have the force of tension like this. Yeah. All right. And let me just mark in the angles and so on. Let's see. I could put an angle. Oh, yeah. No, I'll do the angle like this. Yes. So this angle will be phi. And in general, the pendulum, the bob of the pendulum will have two types of acceleration. It will have radial acceleration, and it will have tangential acceleration. Right? Because as it swings, it's speeding up until it gets to the bottom, right? But it's also following a circular arc, so its direction is changing, so it has a radial acceleration as well. See if I can focus that a bit better. Okay. So I can set up Newton's equations in these two directions. So in and I know this is the tangential direction because that is the direction of the velocity. So the direction of the velocity is the direction of the tangential acceleration. I mean, along that line. So along that line, I get F net equals ma. So yeah, so I would get mg sine phi is equal to ma tangential if I'm just looking at magnitudes. And in the radial direction, I would get ft minus mg cosine phi is equal to ma radial. But I can rewrite, so I can solve for ft. So I get ma radial plus mg cosine phi, but I can rewrite a radial as either v squared over r, or I can write it as omega squared times r, and the mg cosine phi. So there's an overall minus sign difference, but this is, yeah, this is basically the same thing. Does that help? All right, other questions?
Is there any physical meaning to it being negative?
Oh, that's a good one. Let me think. Let's see. So this was our L nu.
Maybe it's because the magnitude of the force of gravity was defined to be positive. So being negative, that means it's essentially acting in the opposite direction. Because we originally defined our potential to be, oh wait, no, force of gravity is negative, isn't it? Never mind that then.
I'd say it's, well, no, I think it comes down to just, it's one of the slight flaws, unfortunately, of the Lagrange multiplier method. So, because if you think about it, this constraint is not unique. All right, I could equally write it as L minus R equals 0. I could write it as 7 times bracket R minus L equals 0. Right? And those are all really the same constraint. So, so that is the slight flaw with the Lagrange multiplier method, is that your value of lambda is going to be proportional to your force of constraint. But if you, for instance, put out a 7 over here, then you would get the wrong magnitude by a factor of 7. Or you would, I think you would get 1/7 of the actual force. Or here, depending upon whether you write R minus L or L minus R, you get either a positive or a negative value. So errors like the 7 are easy to avoid, but the minus sign, I'd say, is until you do the problem, it's hard to tell.
In the book, I know it's a different example, but on page 280, at the end of the example, it does give a reason for why the lambda has a negative sign. So there must be some interpretation.
What is the page number again?
280.
280.
It's a different problem, but maybe it can.
Yeah, no, that's a good point. 280. I'll think about that a bit further. Okay, but yeah, I'll think about that a bit further. But the general result is that if you use this method of Lagrange multipliers, then lambda times partial f. So if you're looking at for the x component of the force of constraint, then lambda times partial f partial x is equal to force of constraint x component. And if you do lambda times partial f partial y, that's the y component of the force of constraint. And so here we were looking for the r component, and f was just that relation r minus l equals 0. So the derivative would just give us a 1. Actually, yeah, no, I think then it's a combination of, yeah, no, okay, good. Thank you, both William and Sam. It's a combination of both those results. So basically what we found was that FR, the R component of F was minus mg cosine phi minus m L phi dot squared. And that is because this force of tension is pointing in the negative R direction. It's pointing inward. So yeah, what we found was the component, and it's pointing in the negative R direction, so that's the minus sign. But the warning still holds that you should be careful when writing your constraint.
If you'd written the constraint the other way, as in L minus R, then the negative sign would have come back out, and we did the partial derivative of f with respect to R. So it would have come out to the same thing, I think.
Yeah, no, the minus sign would not be a problem, that's true. But let me see, would the factor of 7 have been a problem?
Nah, it gets canceled out in other places.
Oh, okay. Oh, then I guess it's more foolproof than I expected.
The real question is, what happens if I did f equals r minus l squared?
Oh, goodness. Yeah. There are, yeah, there are things about using the simplest form. Yeah, you can take a geometrical interpretation that helps you figure out what is the appropriate form of the constraint to use. Basically, if I remember correctly, the idea is that if you take the derivative of your constraint and evaluate it on the constraint surface, it should be non-zero. So, for example, if I do partial r of r minus l, I just get 1. But if I do partial r of r minus l squared, I get, so here I get 2 times r minus l, and then when I evaluate it using the constraint r minus l the whole squared equals 0, this would also turn to 0. So if you get a case like this where it's either 0 or undefined, like if you tried like 1 over square root or something like that, you avoid those kind of formulations of the constraint. What you want is a version of the constraint where you take the derivative and evaluate it on the constraint, and you get a finite non-zero number.
Okay.
There's a geometrical interpretation that can be given to that. It's quite interesting, but yeah, that's going further afield. All right, let me do one more example, but first, any other questions on this one? All right, so let's try that other example that I mentioned earlier. So let's say we have something with a circular cross-section rolling without slipping down a fixed ramp. Let's not make it complicated this time. So let's call this alpha. We'll call the angle through which it rotates, let's call that theta. It's got a fixed radius r. And we're going to call the distance down the ramp as z again. So this time our constraint is z minus r theta is equal to 0. So this is our f. Anything else I need there? And this is fixed. Okay, so yeah, so it's something with a circular cross section. So it could be a sphere, it could be a shell, could be a hoop, could be a cylinder. Yeah, all kinds of things. So we'll say that it has some moment of inertia. And so again, going back to mechanics, so we know L is equal to T minus U. And for our T, we now have 2 contributions. We have 1/2 mz dot squared, which is the kinetic energy of the center of mass. But then we also have the rotational kinetic energy, 1/2 I theta dot squared. And finally, minus U. And, yes, okay. So for that, let's call that height h. Let's call that height, well, the height of the object, let's call that y. So this would be minus mgy. But then we can express y in terms of h and z. So let's see. H minus y over z is equal to, so that's opposite over hypotenuse, so sine. So that is equal to sine alpha. And so I can solve for y. Okay, so let me plug in for y. So I have L is equal to 1/2 m z dot squared plus 1/2 I theta dot squared. minus mg, and for y, I have h minus z sine alpha.
That's a bit low. I can't quite see that.
Oh, sorry. Thanks. So this is my L, but I still need to add on the constraint and the Lagrange multiplier. So my L new is all of this plus the constraint. So I have a plus lambda, and my constraint is z minus r theta.
Is y in the h direction or perpendicular to z?
Y is in the h direction. Yeah, that's a good point. I'll just put little axes here. All right, so again, we see that we've made a trade-off. Really, we only needed one of either z or theta, right? Z would be the usual choice, and we could have eliminated theta using this relation, and then we would have had just a single general coordinate, and this would have been shorter and simpler. Well, maybe not shorter, but yeah. So what we did instead was we did not get rid of one of the coordinates. We kept both of them, and we introduced lambda further. But the trade-off is we're going to get information about the force of constraint. All right, so let me write the two equations. So one of them will be for z. Okay. And so on this side, I get mg sine alpha and plus lambda. Yeah, minus signs go away. Yeah. Yes, and I have d by dt of with respect to z dot only appears in one place, so I'll have an mz dot there. All right, so that's one equation. And then I have partial L nu partial theta is equal to theta dot d by dt. And what does that give me? So theta only appears in one place, which is in the constraint part. And so that gives me minus r lambda over here. And on this side, I have d by dt of, and I only get one term here, I theta dot.
Could you return to the Lagrangian just for one moment?
Yeah, sure.
Sorry.
No, that's all right. So we're using the new Lagrangian.
Yes. Okay, and so we haven't found I yet.
That's correct.
Okay, thank you.
Mm-hmm. But I is a constant, so we don't have to worry about when we're doing derivatives and stuff. Okay, so yeah, okay, those are the equations we need. So I can, oops. So this is equation 2, and then equation 3 is just our constraint, z minus r theta equals 0. That is equation 3. All right, so now I apply the constraint. So I get an expression relating z and theta. And let's see, what should I eliminate first? Okay, so I get theta is equal to z over r. And so theta dot is going to be z dot over r. And then I can plug that in over here. So equation 2 and 3 end up giving me minus r lambda is equal to d by dt of I times z dot over r. Both I and r are constants with respect to time, so I can pull them out. This just becomes z double dot. So I have minus r lambda is equal to I over r z double dot. Okay, and then I can use this back in equation 1, where I have z dot and lambda, so I can eliminate lambda in favor of z dot, well, eventually z double dot, and put that together. So let me just do that. So if I call this equation 4, then 1 and 4 will give me mg sine alpha plus lambda. So it's minus I z double dot over r squared is equal to mz double dot. And I want to solve for z double dot, so I pull those terms together, pull out common factor, divide over, and I get z double dot is equal to mg sine alpha divided by m plus I over r squared. And since I have this equation relating lambda to z double dot, I can use that. Let's see, do I want to? Yeah, sure. So then I get lambda is equal to minus mg sine alpha I, and then the denominator gets multiplied by r squared, so I get I plus mr squared over here. Now, right now, this doesn't seem terribly illuminating, but usually for an object with a circular cross-section, we can say something like I is equal to some constant, call it c, times mr squared, right? If it's a hoop, it's just mr squared. If it's a solid disk, it's 1/2 mr squared. If it's a solid sphere, it's 2/5 mr squared. And so on. A hollow sphere is 2/3 mr squared, so on and so forth. Right, so it's just some number times mr squared. So if we plug that in both cases, so then our z double dot is going to simplify a little bit, because I over r squared will just be mc. You could pull out m or cancel, so you get g sine alpha over 1 plus c. And then similarly, lambda over here, let's see, so we'd have 1 plus c, and the mr squared goes away, and c. I believe we get minus mg sine alpha c over 1 plus c. The form of lambda might still seem a little strange, but we should recognize this as, yeah, this is the acceleration for an object rolling without slipping down slope. And we can kind of double check it by putting c equals 0. That's when it's not rolling, it's just sliding, and we get g sine alpha there. That makes sense. And this force, since this is really lambda z. I mean, this is going to be the z component of the force. So in other words, the force of constraint along the slope, which turns out to be the force of static friction. So yeah, that is the force of static friction. Questions? Okay. All right. Last couple of things. So let's see. Right. So last couple of things are, we know that the Euler-Lagrange equations are of this type of general form. And typically, not always, but typically, the only place where you have an x dot dependence is in your kinetic energy. And this derivative inside here, this ends up usually being a momentum. And typically the x dependence ends up being, this derivative ends up playing a role in the potential energy term. Now, of course, these aren't hard and fast rules, because if you look in polar coordinates, then you do get terms here from the kinetic energy. Similarly, you can get stuff here depending on like magnetic forces and whatnot in like potentials and so on. But by and large, this is something like momentum. And we know that the derivative of potential energy with respect to position, well, that's related to force. So we tend to call this generalized force. And